Hello and welcome to the Data Engineering Podcast, the show about modern data management. What are the pieces of advice that you wish you had received early in your career of data engineering? If you hand a book to a new data engineer, what wisdom would you add to it? I'm working with O'Reilly on a project to collect the 97 things that every data engineer should know, and I need your help. Go to dataengineeringpodcast.com/97things. That's the numbers 97 and then things. To add your voice and share your hard-earned expertise. And when you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With their managed Kubernetes platform, it's now even easier to deploy and scale your workflows, or try out the latest Helm charts from tools like Pulsar, Pachyderm, and Dagster. With simple pricing, fast networking, object storage, and worldwide data centers, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode, that's Linode, today and get a $60 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. You listen to this show to learn and stay up to date with what's happening in databases, streaming platforms, big data, and everything else you need to know about modern data management. For more opportunities to stay up to date, gain new skills, and learn from your peers, there are a growing number of virtual events that you can attend from the comfort and safety of your home. Go to dataengineeringpodcast.com/conferences to check out the upcoming events being offered by our partners and get registered today. Your host is Tobias Macy, and today I'm interviewing Dr. Chris Mitchell and Dr. Thomas Cornu about Audio Analytic, a company that is building sound recognition technology that is giving machines a sense of hearing beyond speech and music. So, Chris, can you start by introducing yourself?
Yeah, sure. So, Chris, CEO and founder of Audio Analytic.
And Thomas, about you?
Hi, so Tom, data engineering lead at Audio Analytic.
And so going back to you, Chris, do you remember how you first got involved in the area of data management?
So I did a PhD in audio classification. So I suppose that's the place where you could say I got my start in it, largely sort of dealing with all of the fun constraints of academic research, which is sort of smaller data sets than you'd like, but still larger than you're used to dealing with, as well as all of the fun challenges of building the technology and doing the fundamental science as well. So that's where I got my start.
And Tom, do you remember how you first got involved in data management?
Yeah, similar thing to Chris. It was during my PhD, I was working with different data sets and, just dealing with them more on disk and stuff, and then moving to work at Biology Institute and working more with computer vision and realizing that kind of having massive data sets just on the file system is not great, and then moved to Audio Analytic where you see a new way of doing things. Yeah.
And so in terms of Audio Analytic, can you give a bit of a description about what it is that you're building there and what was your motivation for building an AI platform for sound recognition and getting the business started?
Yeah, sure. So sort of said, I did some research in the field and found that people weren't tackling sounds. There was a lot of work going on in the speech field. There was a lot of work going on in the music field, and obviously the broader classification field, so image and text, etc. But sound itself has its own set of unique challenges. So I don't know, in comparison to, say, speech, you don't have language models to work with, so you can't constrain the acoustic patterns you're looking for in that sort of way. And you have very large open set data sort of problems. So obviously the sounds that you're looking to detect, you also try and differentiate them from the large number of other sounds that can happen in the world that can happen at any point. Obviously, sounds are relatively random in that respect. So what I was interested in is, could you make a sound recognition system that could capture a broad sense of hearing? So that's normally around a range of target sounds to be detected. So whether it be safety and security target sounds such as glass break or smoke and CO alarms going off, whether they be sort of health and well-being sounds, sort of coughing, sneezing, that sort of thing, or whether they be entertainment sounds or whether they be communication-related sounds, you can start looking at this world of sounds, and then you can imagine what could you do from a product design perspective if products had the sense of hearing, and whether that be mobile phones, headphones, whether it be smart speakers or whether it be smart home. Giving it that sense of hearing means that those devices can respond more naturally in the way you and I would do if those sounds were happening around us, and then they can take intelligent action. So that was the sort of the motivation for it. At a personal level, the motivation for it is I just like machines that make strange noises. So it's quite a natural extension for me to like machines that can classify those noises into various different classes and give the outcome. So quite a sort of a visceral personal love of sound.
And you touched a little bit on some of the contexts in which your product is being used, but can you give a bit of a taste of the types of use cases that it's intended to empower and some of the ways that it's actually being employed?
Yeah, so if we take, let's do it by device is probably the easiest way. So if we take a device like a smart speaker and you want to be able to turn it into a sort of home security device, and you want to know if somebody's breaking into the house from the sound of the windows being broken as somebody enters into the property, then listening out for that sound. There's 4 different major types of glass: laminate, plate, wired, tempered, different sizes, different thicknesses, obviously breaking with different implements. So you're very quickly into a large data management problem, and that's just dealing with the target sound, let alone all the non-target sounds, such as, I don't know, if you've got cats, them knocking things off the work surfaces in kitchens that may be confusable with the types of sounds you're trying to detect. So that's a sort of a smart speaker side on what's called audio event detection. So that's detecting specific sounds, in that case, glass windows being broken. If we move on from event detection to something like scene detection, so this isn't a single sound, this is a sort of a combination of sounds, or could be called sort of soundscape detection. That might be around detecting whether it sounds like somebody's at a train station or at a coffee shop, a sort of whether it's a physical scene in that case, or whether it's an acoustic scene. So whether it sounds calm, whether it sounds lively or not, or indeed whether it sounds like it's inside or outside. Those would be examples of acoustic and physical scene detection itself. And both of those sit under what's called sound recognition, which is the field in which the company leads.
And it seems that at least a majority of the use cases that you're discussing now are more consumer oriented for people to be able to take advantage of some of this intelligence to enhance their sense of well-being or get some sort of feedback about their environment. I'm wondering if you've also experimented at all with use in industrial contexts where particular types of sound might be indicative of some type of imminent failure in terms of structural or issues with manufacturing, or maybe in mining where certain sounds might be indicators of some type of physical risk. I'm wondering if that's something that you've looked at all, or something that you're intending to branch out into.
We obviously looked at, when we started, a whole range of different applications of the technology, given it was sort of a foundational technology in that respect. Yes, we looked at what the area you're describing might be, for me, would be called predictive maintenance or something of that nature. The commercial activity of the company is largely focused towards consumer electronics. It's where we've had the most success commercially, wide scale, adoption. So that's the bulk of the commercial effort that then obviously translates into the thrust of the sounds we're detecting. Most of this world can be described in terms of breaking it down in terms of the type of sounds. So obviously the sounds you'd get in a production plant, I think, is the example you'd use, would be very different than the sorts of sounds you and I would care about in our house, or if we're out about on the street. They just end up being very different sounds, and we capture that in terms of the taxonomy that we use to structure our data.
And my understanding of the way that you actually deploy your product is that it's an embeddable AI model that other companies can license and include within their own products. So I'm wondering what types of challenges that poses in terms of the deployment mechanism and the types of interfaces that you provide to those companies to be able to take advantage of your technology, and just issues in terms of updating the model definition if there are any changes or enhancements that you make to it.
On the for sound recognition, because inherently sound goes hand in hand with privacy concerns for obvious reasons, we believe that sound recognition under a large range of use cases is best done at the edge of the network. obviously all the audio data can stay there for means of classification. You don't need to transmit it off the device, which gives you cost and other economic benefits and scalability benefits. In terms of the more on the con side of that approach, clearly you don't get to update the models as quickly as you would if it was a SaaS-based model or something like that. We don't tend to see that being much of a commercial issue. Most of the firmware now on consumer electronics devices is updated reasonably regularly, but we also know that when the customers do want to get that updated, it's something they can easily push out to the end users. On the general point of getting the challenges it faces, it means that you need to know quite a lot about the subject matter variability that you're trying to detect. So that's where the quality of the data sets comes in. But generally, consumers don't tolerate lots of failures out of classification systems, and especially not around the fault tolerant sort of aspects of security or safety, where if I told you, Tobias, your house was being broken into now because I heard a window being broken, if you rushed home, if you're not already there, which is highly like you are given circumstances, but if you did rush home and find out, you're not going to tolerate many of those as false alarms. So actually you want the models to be pretty well structured and understanding most of the variability they're going to come in contact with. Otherwise, the overall value proposition doesn't work very well. So that sort of that aligns with this notion of being edge-based in the large number of use cases that are applied to sound recognition.
And given the fact that you're building these AI models and everyone knows that it's garbage in, garbage out, and you highlighted the fact that you have to ensure a high amount of quality in the input data, and I'm wondering what are some of the unique challenges that you are facing in terms of being able to collect and label and create a taxonomy around these arbitrary sounds and being able to ensure that you can correlate them with some sort of meaningful event.
It's a great question. Let me just, I'll give you the broad brushstrokes, and then Tom deals with this on filling out that taxonomy. Obviously, part of the great job he does is around sort of doing what we call sound expansion. So on the taxonomy side, we break things down at the top level into three parts. There's anthrophony, geophony, and biophony, but there's sort of 700 label types that we're dealing with on a daily basis inside the system. So a label type would be something like a glass window being broken or a smoke or seal alarm going off. So this is a large set of classes you're dealing with on the target and non-target sound side. On the before Tom answers the sort of practical problem on the AI side, there's also a range of specialized things you need to do on the AI. So clearly, if you take an off-the-shelf speech recognition system, the acoustic model is designed for our voice box, and clearly a large number of the sounds we deal with aren't produced by humans, and an even larger number aren't produced by humans using their mouths. So there's quite a lot of issues there on the acoustic model side. And then, as I said earlier on, that language model that the speech recognition companies rely on very heavily, it sort of does quite a lot of the heavy lifting in correcting the errors made by the acoustic model. Clearly, when somebody breaks your window in the example I'm using, it's not trying to speak to you in any structured way. So you don't have that language model. So there's also fundamental AI things you need to solve before you even start, which you can only do with the good quality data. So you need to both get the garbage in, garbage out principle sorted, and then you can study the AI principle off the back of that. And the sort of the out of the box techniques don't work. In terms of the day-to-day stuff, Tom, you're best placed to sort of explain some of the challenges we face there and the tools we do use to overcome it.
Yeah, sure. So, I mean, for most of the stuff we work on, like a data collection, you can consider as like a project type approach. So we'll be given some notion of a sound that we want to work on, and we'll attack it in different stages. So the first part will be kind of considering like the spec that we want to develop for it. So perhaps for certain sounds we're more strict around certain criteria, and then for other sounds less so. And that spec's really going to be important in kind of guiding us through the rest of the process, in terms of like how we go about the data collection, right through to like the labeling and the metadata associated with it. So you can consider that, for example, so like something perhaps like a dog bark sensor, you can consider all of the different degrees of variation that dogs exhibit, if you like. You'll have small dogs, you'll have big dogs, different breeds. Perhaps the age will affect the sound of the dog bark will the dog will make when it barks, and other sorts of factors. And so that's like, for each sound that we work on, we have to do this massive sort of brainstorming exercise around making sure that actually the data we're going to gather is going to be valuable. I guess in a similar way with speech recognition, when you're designing data sets, right, you have to sort of make sure that they're sort of have all of the different sort of phonemes or whatever it may be that you're interested in. So then we'll have developed this plan for like the data that we actually want to collect, and then there'll be like a stage where we then have to essentially source this data. I mean, unlike some sounds, like perhaps if you're doing a smoke alarm type sound where you can buy the sensors for a dog, you can't just get a dog off a shelf, as it were. So you have to source these dogs in some way. And so we'll reach out to like the volunteers that we have. So we'll have got a global volunteer network, and so we can draw upon those people to provide us the sources for these sounds. And so we're able to just email these people, and for some amount of money in return, they'll be able to provide us with a dog in this situation. So we'll line up a load of people to help do the recordings, and then a situation like that will probably go into our anechoic chambers at our sound lab or semi-anechoic chambers, and make sure we record the sounds, to a really good standard, as you said about the garbage in, garbage out. But of course, you can consider there's a few sort of, again, bits of variation there that you've really got to focus on. And one of the areas will be the different channels or the microphones, if you like. But you can also consider, for example, something like with a dog, that's going to be running around and moving about, and so that presents its own sort of challenges. And each, I have to say, and kind of my experience working at the company, no one sound is really. There's always challenges that you don't expect when you first start working on these things that you kind of have to overcome to be able to do a good job with those sides of things. And then we've spent a load of time then gathering a load of really, really fantastic data, and then you have to process this data and label this data. And the labeling is a really important aspect for the sound recognition problem. Just deciding on how you want to do the labeling. Do you make sure it's extremely sort of fine grained, or can it be more coarse, or can you use like weak labels and stuff? And then so that once we've kind of gone through that stage, so we can make sure we get it into Alexandria, our data platform for storing all of this data. And I think it's one of the things that every stage in that kind of this really just the data aspect of the pipeline is kind of each part has its own challenges, and you have to get a lot of things right to make sure that the data that you then can present onwards to the machine learning teams is of the sort of best standard that you can really get.
So because I know, Tom, you've got 15 million pieces of audio data in Alexandria, 200 million pieces of metadata, and 700 label types or so. I think, Tobias, one of the interesting things to realize is labeling audio data as opposed to speech presents its own set of challenges, as Tom talked about. So even if you take something as basic as baby cry, and Tobias, I don't know if you're a dad or you've got kids or anything, but if you sit down a bunch of people and you say, tell me when, here's a recording, tell me when the baby starts crying, when it stops, most people will disagree each other. They'll agree in the main, but at the edges, when you're trying to do, 10 millisecond labeling accuracy around when a baby started crying, you'll get into debates like, is it crying? Is it grumbling? All the things that you would do as a parent start to come out, because that audio is just less exact. Was it in a speech world? It's a lot more exact. You can take a typical person off the street and say, label the words and when they started, and there'll be very little disagreement in comparison. And that gives Tom and his team some sort of fundamental challenges with labeling up these sort of things, which I know they spend a whole bunch of time just figuring out, how do you label a new type of sound? What is that sound? And when does it start and when it stops?
And the metadata aspect, too, is interesting because with things like textual records or structured data, it's easy to associate the metadata with the record at the time that it's being created. And with image data, there's the standard of the EXIF tags. And I know that, for instance, with MP3, they've got ID3 tags, but I'm wondering if there's any sort of useful standard that you can use for embedding the metadata with the records, or what your approach is for being able to effectively associate that information with the actual audio segment and ensure that they propagate through your system in conjunction with each other so that they're easy to relate to one another.
So we have a whole subject. We call it audio provenance, and it's a whole subject matter for us internally. The two examples you've used. Let's take image data. If I showed you 3 pictures of a toy dog and one of a real dog, you'd very quickly be able to identify with no prior information that's the toy dog. Those are the real dogs. Audio is much more complicated than that. We're very much attuned as humans to sort of fill in the blanks. And so, I could play you 3 recordings of smoke alarms and say one of those is a fake smoke alarm, and I guarantee you'd be very bad at telling me which one was the fake and which one was the real one. So if, for example, I don't know, you scraped a bunch of audio files off the internet, you'd be straight into that garbage in, garbage out principle. By doing that high quality data collection inside those semi-anechoic environments, it means we're there when the subject matter variability is explored. And then you're right, that sort of chain of evidence, if you will, has to be passed all the way through the pipeline, right through the data collection, processing, labeling, augmentation, training, evaluation, even sometimes down to the compression and deployment levels, so that that it's doing a good job. In terms of frameworks for doing that, no, there's no off the shelf frameworks. That's a completely new area itself.
And yeah, with audio data, there's definitely a huge degree of variability along a number of different axes where, as you said, you've got your anechoic chambers for being able to isolate the sound to the specific piece that you're trying to collect, but then out in the real world, that's going to often be overlaid with whatever the other background noise is, whether it's the, hum of your washing machine in the next room or the sounds of engines going by outside, and then being able to isolate that sound. And then for your volunteers who are contributing the audio that you're using for this collection process, I imagine that there's variability in terms of the quality of the microphones that they're using, the sample rates that they're collecting the audio in, the specifics of the audio format that it's being collected, the lengths of the segments. I'm wondering how you approach being able to try and encapsulate all of that variability and be able to standardize it in some way for being able to feed it through your model training process.
In general, you're right. We think about it in terms of subject matter variability and channel variability, with channel variability split into 2 parts, which is sort of a acoustic coupling variability, which would be the environment you're in, the acoustics of it. Is it a reverberant environment? Is it in the bathroom, or is it sort of in the hallway? And then you've actually got the actual device channel variability, which includes the microphone. It includes all of the various parts of the audio subsystem before the input audio is received at AI3, which is the inference engine that we run to do the high quality sound recognition we do on the device. Tom, in terms of the challenges with all that, if you want to pick that piece up.
Yeah, sure. So so you're absolutely right in terms of it's a massive amount of data to try and encapsulate. If you consider all the things you've talked about and then sort of draw it back to just one single file, and for one single file, as you said, you'll have the particular sampling rate, the particular bit depth, the particular channel it was recorded on, a bunch of settings around, whether it's the device you were using to record or the sound card. Then you'll have stuff like the room it was in. Perhaps, like you say, is there some sound in the background that's going on at the same time? Obviously, this will be in situations where we're kind of recording in situ versus, say, in the anechoic chamber. And then around, exactly like the source variation, the gender of the dog, the age of the dog, all these sorts of things. And so in terms of capturing that data, we've got tools that sort of help us, I would say, kind of structure the collection around this, but you consider it's still quite a manual effort of you still have to kind of match up. When a volunteer comes in, you have to put in the name of the dog in a particular record and sort of make sure that that's stored along with the correct file. Now, when you consider, say again, going back to the dog example, if you record one particular dog bark, you might be recording it with, some several tens of devices at the same time. And so you need to make sure that the information around the dog is kind of propagated to all those, say, 50 odd devices. But then the information about the individual devices is kept specific to the devices. And so, we do have a pairing of a chunk of metadata with each individual sound file. And you can imagine that, those numbers grow pretty vast in terms of how many kind of elements of metadata we have a record of.
And in terms of the taxonomy that you're building for being able to track and categorize these different audio segments, what was your approach for structuring the initial taxonomy, and how has it had to evolve, and what are the assumptions that have been challenged in the process of building and growing that taxonomy for being able to make that information useful in some sort of structural or hierarchical way?
So the taxonomy is structured on what's called an actor principle, which is why that sort of anthrophony, biophony, geophony, the top level thing. So obviously caused by humans, caused by geography, if that makes sense, and caused by biology. And then it cascades down from there. The actor principle is a fundamental one. It was a specific taxonomy principle we came up with because obviously something needs to cause those sounds in the environment. So using that as a fundamental building block means that you're not going to go far wrong. In terms of skipping to your last question, in terms of things that we've, I suppose, effectively learned that we didn't know we were going to have to learn, one of my favorite examples of that is not realizing sometimes the sound world conspires for you and sometimes it conspires somewhat against you. So there is a smoke alarm that's, I think it's the third or fourth most popular selling smoke alarm in North America. And it sounds identical to a bird species in the south of France. Now, I'm pretty sure that bird species hasn't evolved to mimic the smoke alarm, but that sort of then thing that is then presented to the machine learning engineers and saying, well, these things sound pretty much identical to humans, but you need to separate them out. Otherwise, people are being told that their houses, the smoke alarms are going off, when in fact it's just the bird that they keep in their living room tweeting away, and it happens to sound identical to this North American smoke alarm, which the engineers solved. But that those sort of interesting quirks of, I suppose, fate, if you will, are fascinating to experience, although do give Tom and the rest of the team sort of, I'm sure, sleepless nights of worry as they try and figure out how to best collect the data and best separate it out.
And another element of this problem space is that a lot of the tools that have been built for being able to work with and process large volumes of data are generally oriented around textual and structured data. So I'm wondering what you've been able to use in terms of off-the-shelf components for being able to actually process and build these models, and how much of it you've had to custom build in-house specific to your use case and your problem domain.
Sure. Yeah. So, I mean, you're absolutely right. Like, I mean, a lot of the tools when it kind of comes to the audio world, I say audio and then kind of bridging a bit into machine learning, are really kind of for speech recognition type applications or kind of music oriented stuff. So you might have, for example, some tools around transcription, sort of aiding with transcriptions for speech recognition type problems. But obviously, as Chris has touched on a few times, speech sound isn't speech. And then the other way you can consider, there'll be, even software, say like Audacity, absolutely fantastic at doing the job it does. But again, it's specific to music, and in this case, kind of recording and music production and that sort of things. And so often it's what the problem that we're trying to solve is quite specific and it is difficult. There is an element of having to roll your own or enhance if you can. Of course, it would be it's easier, it's more time beneficial to do it that way, enhance. But if you have to kind of roll your own, then for a lot of stuff that we work on, we do kind of have to roll our own. I mean, consider the example of recording with many devices at one time. There isn't a magical start button that allows every single device to be started at the same time and stopped at the same time, because, well, actually, if there is, we'd like to hear about it because that would be extremely useful. But you have to solve, you kind of then have to make sure that the audio, obviously, if there are then like different offsets at the beginning of the file, that the sounds occur in the same part of the audio across the many different devices. And so we've developed techniques to handle that problem, ourselves. And yeah, I guess, right through the pipeline, we have got, a lot of stuff that is bespoke to us at Audio Analytic to just help solve those problems that aren't quite the same as in other areas.
And can you dig into a bit of how the actual data pipeline and data management is architected and the ways that you work with it for being able to train and build and deploy the models that you're working on?
Yeah, sure. So I mean, so in terms of like, the whole pipeline of what we do at Audio Analytic, you consider it as standard sort of machine learning delivery pipeline, and so we go through from the data collection right at the beginning through to the deploying of the models at the end, and there are many stages in between there. So focused around, say, Alexandria, which is our massive database. The stage of the pipeline will focus on kind of around the data collection side, as I've touched on. The processing, like with all these, you've got many different devices and many different formats that the audio come in. Some devices will give it to you as one format, and others will give it to you as another format. You'll have to then the next stage will be that, like we said, the labeling part, and that's where you kind of marry up all of the metadata and the labels and the sound, get it into Alexandria so it can then be made available for the machine learning teams. And then there'll be a stage in between there of you've got to consider as well. It's not just a bunch of audio data in a data set, or from a data set you download on its own. It doesn't necessarily give you that much. You've then got to kind of say, right, let's split it into those machine learning sets where we need to make sure that ultimately the stuff that goes in that testing set is representative of what our real world situation is going to be, and then you need to make sure you've got the same kind of distributions throughout. And so that's another very important aspect of making sure that you gather enough variation all across the board, so that when you chop it up into these little sets, that you've got it in the right places. So that's the point that the machine learning team will take this stuff, and so they'll apply techniques like data augmentation, to further increase the volumes. I mean, machine learning models nowadays are so data hungry that you have to kind of apply these techniques. And then look into the training. You've got lots of different model evaluation type procedures going on, and then you'll have like a more formal evaluation stage, then kind of deciding on what sort of models that you're interested in, or what trade-offs you're making, I guess, would be a better way to sort of structure that. You'll then look at trying to compress these things. As Chris said, we run on the edge. You can't have massive models that take tons of computation. That they need to be really small. They need to be really, really fast. We're not the only stuff on these devices, right? There'll be other sort of functionality that these devices will have, and we're just one part of the stack, if you like. Yeah, and then that kind of leads into the deployment side of things.
In terms of optimizing that pipeline, in that sort of evaluation stage, one of the interesting things we've done recently is around something we call polyphonic sound detection score. We found that like with any challenge, you need to optimize, any machine learning challenge, and probably more broadly, you need to optimize for the right criteria. And the generic methods that were being used, just borrowed from machine learning, were not optimizing the systems appropriately, and the pipelines and everything else. So we released a bunch of GitHub code for this polyphonic sound detection score. That's now being used, I think it's published at ICASP this year. It is being used as part of the DK's competition, which is sort of the benchmarking world. This is the standard, if you will, community standard of sound recognition. So it's great to see the discipline grow out of its infancy into those more developed areas and moving into what we start to call second generation sound recognition.
And in terms of the models and the deployment of it, I'm wondering if you just deploy one model that works generically across all the different sound categories that you have collected, or if you train these models for specific deployment targets where you have one that's specifically focused around security, where it has things like the glass break or sounds of, a door being hammered on. And then you have a different model that you deploy that's focused on things like detecting a cough and sneeze and sniffles for health-related environments.
So it's a great question. So we tend to think of the sound profiles, as we call them, which is a one or a collection of sounds broken down per device, because the value propositions tend to align at the device level. And then, of course, you can run multiple sound profiles together. In terms of those configurations of those underlying models, it really comes down to the individual use cases that are applicable on the devices. But we try and make sure that end set of sound profiles we're delivering are optimized for that set of use cases for that set of devices.
I imagine that helps too with restricting the size of the actual deployed model rather than trying to fit everything into one thing and then also compress that down to a size that's runnable on an embedded device versus just training the model for a specific use case and then reducing the overall scope of what it needs to be able to handle and thereby the size of the model that's being deployed.
Yes, size is somewhat proportional to the amount of sounds that you add, especially when you're dealing with a smaller number of sounds. So as it grows, that sort of relationships becomes less distinct. In terms of course, if there's sounds that you will never come across and never need to detect on a device category, it would seem a bit silly from a computational point of view to burden that device for looking for those sounds. So yes, it definitely helps in that notion that this is about sort of structuring a sense of hearing in line with what is needing to be heard for those device categories and sort of a just enough type approach that means that you have that good trade-off between computational smallness or sort of resource size and that sense of hearing. So in fact, we did a recent set of things at the Consumer Electronics Show this year in Las Vegas on our private demo suites, which was showing that we were capable of running a sense of hearing right down onto an M0 plus processor, which is the smallest grade of processor that the ARM do. So really showing that you can push that sense of hearing down onto incredibly small processors.
And then in terms of being able to actually evaluate and test the models that you're working with, I'm wondering what you have found as far as their capability of operating in noisy and complex and layered audio environments and how the overall testing of the model has fed back into your strategies for collecting the source data.
So if I take the top piece and then Tom, if you could relate back to the source data piece. So in terms of that feedback, so generally because we've got the world's largest collection of data for this area. We have high degree of certainty with the models we're providing to the marketplace already. We have large amounts of, say, 24/7 recordings, large amounts of environment recordings, and obviously large amounts of target sound environments. So we typically find that we're pretty good in our guesses of what the performance will be for a new sound profile that we're producing. In terms of the sort of things we learn, going back to that example of things that you just can't predict, I was using the example of the bird in the south of France and the North American smoke alarm. That is something beyond the wit of man to sit in a room and figure out. You're only going to get that sort of insight from the actual field deployments. Our technologies deployed in something like 160 countries worldwide, so we've got a very good sense of the sort of problems that are faced on a worldwide scale. In terms of how that feeds back, obviously it feeds back into, do we need more data in a certain area? But Tom, you're probably best placed to sort of pick back up that full loop back to the beginning of the pipeline, the data collection piece.
Yeah, I mean, well, like you say, it's beyond the wit of man to try and think of all these things. I mean, I've been in, we start these projects, I make sure we sit in a room and think about all the stuff that's going to try and bite us in the backside. And you do just never think of everything. There's too many bizarre things, and your head is so focused on kind of one aspect of looking at the problem that you'll be completely blindsided to another, even though you spent all that time trying to figure it out. And so, the delivering of these products, they are very iterative. You'll develop something and get it deployed, and then you realize you have these sort of issues, and then you kind of have to. I think often, going back to data collection is one of the important ways to kind of address these problems. I think you can consider as well, for example, talking about how do you sort of actually do the evaluations, like as Chris touched on, the 24/7 sort of use case for a lot of our products. We just have absolutely tons and tons and tons of data that is just kind of use case. It's like a product in a room, and it's just recording all that time, and we'll have many different examples of that. And so hopefully you try and identify some problems early on in your kind of evaluation, kind of your product development cycle, by doing tests like that. And then in terms of like the actual problems that you make, obviously that's then kind of focusing more on these the false positive like area of the evaluation. And then in terms of the more like focusing on how well do we actually do with actually detecting the sounds we're interested in. We mentioned the anechoic chamber earlier, and that really allows us to have a sort of green screen for sound. Like you said, you mentioned that you get this layering of background sounds and so on, and really that's a really good way of going about it. Is that, again, let's go back to the dog bark analogy. If you want to know whether a particular model is going to detect a dog bark in a particular, say, room with, say, tile flooring, and it's a really, I don't know, say a really reverberant environment, and someone's hoovering in the background, and whatever else, maybe the device is 5 meters away or something. You have to literally test for that exact scenario. And so by having these green screens, we can sort of test. And again, it's looking at this stuff iteratively, evaluating often, and then feeding it back in and seeing where you can make improvements.
What we find though, I think, is the experience we now have with doing these things means that internal iteration speeds up and speeds up and speeds up. So we're producing sounds at an increasing rate of knots, and those sounds being produced in their first iterations internally at higher quality, just because obviously we're starting from a higher place. So we've learned a lot that iteration cycle means that we can now iterate internally very quickly, so that when we do release that product out into the marketplace, the customer can have high assurance that's already working from a sound recognition perspective, and not thinking, I'm sort of getting a bit of a product, but I'm going to have to feed back data to improve it, because clearly that's not going to be acceptable to their customers.
And in terms of the audio that you're working with, what have been some of the most interesting or unusual or strange sounds that you've had to try and collect and categorize?
I'll do 3 stories. There's strange in just sort of strange experiences of capturing the data. So I'll do that one first. So we did some gunshot recordings. We oddly enough chose to do them in the UK, and machine guns anywhere in the world are not easy to come by, but in the UK they're particularly challenging to come by, and we managed to arrange a set of machine guns to be recorded. One of them was an Uzi submachine gun, and we had a rental van to go down to the there's only 2 civilian sort of automatic ranges in the UK, and we had a rental van to go down there. I remember sitting there with the guy, and he laid out the guns, and he explained that we had to move our rental van. And I said, well, why is it? It seems to be nowhere near the target. And he said, well, the Uzi doesn't so much aim bullets as sort of direct them vaguely in that area. So you probably want to move it before you get a bunch of holes in your van. And I'm pretty sure that would have caused us a whole range of fun, from at least the deposit on the rental van, let alone the explanation to the police, I'm sure would have then come. So that's on the sort of strange data collection experience. In terms of strange sounds, that's a good one. Tom, what's your favourite strange sound that you've done the data collection for so far, that you're able to talk about, obviously?
Yeah, for sure. Well, yeah, again, I guess this is trying to think of individual sounds. I mean, I guess, I guess you come across sounds when when you've got 24/7 data. You might come across stuff like geese honking, which is always quite an interesting one. But in terms of like weirdness, in terms of collection for me, I guess it'll be the outdoor glass break collection we did, where I guess perhaps similar weirdness to Chris's thing, but like, essentially we were tasked with just being on the street and smashing people's windows, of course, with permission and everything else. And we were paying people. We were saying that, we'll give you some good amount of money. You can repair, you can replace your windows that are 20 years old, but we'll break them for you. And it was a really, really bizarre experience. I mean, you're literally in a residential area, and you've got, we put on fluorescent jackets, so we kind of looked like, we were meant to be there, with all these different microphones and all these booms and stuff, and all these wires going around, and then someone smashing these windows with a sledgehammer and this sort of stuff. Yeah, that's how you kind of work for a very interesting company, when you're sort of tasked with something like that. But yeah, that's definitely weird.
The one I'd top it with, we did a car alarm data collection exercise, and we'd done the sort of in-car model fits, but we were looking at the retrofit car alarms, but obviously wanted to know what they'd sound like when they're fit into the car. So we had a board in the back of a car with these car alarms on it. And we collected most of our data, but there was one challenge left, which it was to go to a very reverberant real environment and collect them in there, because we just wanted some, sort of high quality real reverberant. And I remember sitting in a multi-story car park with a car, and these things are very loud as well. So you want to go a bit of a distance away, because obviously the car alarm is unlikely to go off when people are physically sitting in the car, which would dampen the sound. So we're sitting away from this car with a wire sort of trailing from the car with a big button that sets off all the car alarms. And then somebody pointed out this might look a bit strange to the security guards watching us on the inevitable CCTV cameras that would be watching this thing in sort of some bizarre, I don't know, Italian Job kind of blow the doors off type piece, or something more sinister, not entirely clear. And then realizing we better finish our experiment up rather quickly before we caused anybody a whole bunch of the hassle. I think on that one gets interesting, because the recording of audio itself presents a whole range of challenges from a data privacy, data ethics perspective. So if you're trying to do audio recordings in the public, there's a whole set of rules that govern that. Obviously, there's increasing rules and direction of travel around what data you should be able to use in machine learning models, both legally, ethically, and the direction of travel, from a GDPR and the things that are, sort of going through the various stages of legislation. And even if you do something basic, if you want to record a park, when you try and square that with the various laws, you need to get permission to do that. But it's a public park. Who do you get permission from? So you're down into really quite fundamental challenges if you want to make sure that not only is your data good today to be training off, but as the rules change and evolve, and society understands what they want to do with machine learning, that data you've based your models on doesn't start to be eaten away at, and you can't include it, or it's decided that you didn't have the right permissions, or the traceability around the data and what's gone into it isn't clear. You don't want to fall foul of any of those things. So the effort we go to make sure that we've got that complete chain of evidence around our data is quite extreme, and that's been ingrained in us from day one. It's obviously been expensive and time consuming to do, but that choice has paid off quite substantially with the direction that the machine learning world has gone in.
And what are some of the other interesting or unexpected or challenging lessons that you've learned in the process of building out the technology and business aspects of audio analytic?
On the business side, we license per sound, per device, which is the closest in the speech world, would I suppose, presumably licensing either wake words, if that was the equivalent, or language. So there weren't any directly comparable models, because those two are clearly different in various ways. In terms of then, we've had to go out and we've obviously explained to people why sound detection is extremely valuable if you're designing products, and why it gives that very intuitive sense of the device is behaving as you would expect it to. But that's been done from the ground up, and that was a new area for product owners to experience, which means that how they judge how we should license it, how they judge the commercial value, where the value is realized, and things like that has been part of that journey. And that's been fascinating to experience how people perceive and how they think the world of sound should be monetized, I suppose.
And so, as you continue to build out the technical and business capacity for the company, what are some of the plans that you have for the future, either in terms of new problem spaces or use cases that you're looking to reach into, or enhancements to your existing processes of data collection and machine learning?
Our roadmap is largely punctuated by what sounds for what use cases, is the way to think, and we constantly add to that as we expand our ability to differentiate sounds and obviously the target devices capabilities themselves. In terms of future stuff. I think we did a blog post recently on our website. If you go to audioanalytic.com, we did it on what we'd call context systems. So context systems look to not only detect individual sounds but draw larger inferences off those. So the example that was used in that blog post was it sounds like you're leaving the house. So Tobias, if your other house is leaving the house and you know that you've not reminded her to get bin bags or whatever the other sort of small items that you just forgot to remind her of, you will know that. You'll sit on your living room, you'll be able to hear it if it's in earshot, and you'll know what leaving the house sounds like and what preparing to leave the house sounds like. But it's not a single sound. It's a collection of sounds in a certain sequence put into broader context. And that sort of higher level reasoning requires even more sophisticated approaches to sound recognition, and that forms some of the foundations of what we mean by second generation. So first generation sound recognition systems are around a small range of sounds, typically safety and security applications, and typically triggering events through to the end consumer. So there might be push events through to mobile phone. I've heard somebody's breaking into your house. I've heard a smoke and CO alarm going off, that sort of thing. Second generation is about much more sounds covering not just safety and security, but entertainment, health, and well-being. And the starting introduction of these context systems that start to use that fundamental understanding of the individual sounds or scenes that it's hearing, and building higher level inferences on top of them. And that's the exciting world to see unfold as that sort of sense of hearing it becomes more and more real, in line with what you and I would call the sense of hearing. So those devices can be more and more intelligent.
And I'm also wondering, given the fact that you have collected this large volume of data and it's well labeled and highly valuable for building your models, and that's what you're licensing, I'm curious if you've also gone down the path of looking to license out the actual source data for other people who are looking to take advantage of it for other use cases.
No, so typically commercially, people are licensing the models. So we've got this, as you rightly pointed out, Alexandria, which is this world's largest collection of data. It's about 15 million audio files, 700 label types, and about 200 million pieces of metadata. That helps steer where you put your research from an AI perspective. Coming back to those points I mentioned around, there's fundamental architectural blocks from a machine learning point of view that you just can't use, like a language model, like the speech acoustic model, that would materially impact your performance rates and mean that if you just took an off-the-shelf machine learning technique, your performance rates wouldn't be good enough for the vast majority of sound recognition tasks. So we've used that data to steer our research and come up with our own inference engines that are specifically designed for sound recognition. So those two pieces tend to go hand in hand, because even if you have the data, you'd still need to direct all of that research effort to get to a point where you have a well-functioning sort of second generation sound recognition system. So generally people want to license the output of that and take advantage of both of those pieces.
Are there any other aspects of the work that you're doing at Audio Analytic or the overall space of sound detection that we didn't discuss that you'd like to cover before we close out the show?
No, I think you're good. Apart from, I'd love to send you over some bizarre audio files, and we'll see if we can find you some and send them over, just because they're always fun.
Well, maybe we can put some of those interspersed throughout this conversation just to give people something to entertain themselves with. Well, for anybody who wants to get in touch with either of you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as a final question, I'd just like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
So for data management, obviously it's going to be biased because we're solely focused on audio. So most of my concerns are going to be around the audio side. I think a realization that the machine learning frameworks have come on, and the data pipeline side has come on, and the data management side has come on generically. But now we're into the specialisms, and the specialisms require us to extend, hopefully, what are extensible frameworks. Would love to see more of those frameworks becoming more extensible, more modular, so we only have to roll our own pieces in the area that makes sense. A lot of the times we come across tools where they just don't work well together, so you end up, even though there's good bits of functionality in tool A and good bits of functionality in tool B, that you still need to specialize them to the task at hand, and then those two tools aren't as flexible as you'd like them. So if there is one area, it's sort of that digging into each individual task within machine learning has its own set of challenges, and realizing that at a fundamental tool level and baking that into the architecture of the tools that could go across the industry would be incredibly valuable.
And Thomas, how about you?
Yeah, I mean, I'd echo Chris's answer, to be honest with you. It's just as soon as you get into something that's just kind of a bit more niche than the sort of mainstream applications for a lot of these things, you have to start rolling your own. And I'd say that applies to, right across the kind of spectrum of wherever you apply machine learning. Really, it's been my experience before as well.
All right. Well, thank you both very much for taking the time today to join me and discuss the work that you're doing with Audio Analytic and sharing some of your interesting stories of collecting these audio data. It's definitely a very interesting use case and interesting problem domain that you're working in. So I appreciate all of the time and effort you've put into that and the time that you spent sharing your experiences with me. And I hope you enjoy the rest of your day.
Great. Tobias, thanks for having us on the show. Been great. Look forward to listening to future episodes as you go forward.
Yeah, cheers, Tobias. It was great to speak to you. Thanks so much.
Thank you for listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.